And the next presenter is Zach Gerards, who will give a surprise presentation that we completely missed in the labs and lectures, the symmetry of molecules, how it is implemented in Gaussian software.
I'm Zach. All right, so yeah, I'm going to talk about some molecular symmetry applications for Gaussian and GaussView. But first, we need to kind of get an understanding of what is molecular symmetry. So symmetry is simply an indistinguishable representation of an object in space upon the action of a symmetry operation. So when you apply this to molecules, it's molecular symmetry. Now, what are these symmetry operations? Well, there's 5 of them. One, there is the molecule itself, and the matrix representations are there in lieu of actually having some 3-dimensional figure to show you. The other one is a rotation, which is determined by 2 pi over n, where n is an integer number, so this is in radians, right? Matrix representation. Third, reflection. Fourth, inversion, and then the 5th one is really a product of two operations, where you have rotation and the reflection. Okay, so how do we characterize molecules by their symmetries? We do this by point groups. And so this is a nice little flow chart that shows an algorithmic way to assign point groups for different molecules. I'm not going to go through it because we don't have time. But notice the DNH group here, because I'm going to show a molecule that falls into that point group. More or so for completion, I'm not really going to go over this, but this is a character table. What character tables are is they are complete representations of a point group symmetry in tabular / matrix form. And so the reason I show this is, one, this is the table that people who use group theory to look at molecules can predict molecular characteristics or behaviors. And also on this kind of list here, some of you may have noticed some of the functions in your output logs. They actually have these molecule symbols by them. This is where they come from, is they come from the character tables that corresponds to the point group of the molecule of interest. They have meaning, but we don't have time to go over it, unless you want to take group theory, which I suggest some of you should. Okay, yes, now let's go to the actual practical aspect of applying symmetry to GaussView. So, very quickly, we start with our benzene molecule, and to get to the point group dialog box, go to Edit, Point Group. Then, what you need to do is enable point group symmetry. It's disabled by default. And so what are some of the things one can do? Well, you can constrain your point group or your molecule to a point group. So I chose benzene. It is, as it is, D6H is what its point group is, though the default is always C1, which is virtually no symmetry. That's what that point group means. So if I constrain it, and if I want to perform some operation on it, like changing the bond length, since I constrained it to that point group, it will change the bond lengths for everything, even though I just specified 2 atoms in order to maintain the point group. Okay? So now what happens if I have a slightly disordered molecule, or one that is not optimized for its predicted symmetry? So I started with a benzene molecule that is slightly elongated along or a bond. And so go back to the dialog box. You want to set your tolerance. When you set your tolerance, you increase the really the deviation of the molecule as it is to what it could be. So the greater the tolerance, the higher order point groups you would have allowed to. And so I want to get this to D6H. I select 1.0. Do I feel lucky? Never. But so I can click on this drop-down menu, which will list the higher order point groups. Select D6H, since this is benzene, that's what it is. Click Symmetrize. Oh, hey, would you look at that? We are now symmetric. Okay, so how does this apply to things like doing jobs and calculations? Well, if you go to the Calculate dialog box and click on the General tab, you have this little checkbox where you can actually ignore symmetries. By default, it's unchecked. So every calculation you guys have ever done so far in class, symmetry has been accounted for. However, if you don't, what happens? Well, this is maybe not very impressive, but the conclusion's still the same. So I just did the total energy calculation using Hartree-Fock for benzene, the 321G basis set. So with no symmetry considered, the calculation took 1.8 seconds. With symmetry, took 1.5. Once again, not very impressive. However, if one were to do a more rigorous computation, this would become more useful. What's kind of happening, though, in the background is that if you look at the log file, what's being generated are symmetry-adapted basis functions instead of just the basis function that you were initialized with. So what that means is that if your molecule has symmetry, it will more or less reduce its basis set and then project or perform the operation on the smaller basis set and then project that calculation for the rest of the molecule, assuming that it is symmetric. So, conclusions, you can optimize geometry, not so much quantum lengths, more with quantum angles, and reduce job time, while maintaining accuracy.